dimensions like materials, design, and then processes, and also science, understanding of science behind various aspects of additive manufacturing. Right. So I think this workshop is primarily focused on uh, what you call as this healthcare applications, right? So additive manufacturing has been there for quite some time, like 40 years, and the majority of the applications of additive manufacturing in healthcare applications would be covered by the speakers other than me. So I will be taking you or walking you through some of the interesting topics about sustainability and the design freedom that additive manufacturing offers, right? So this has been the topic that I was gave this topic long back. I think at the middle of December or November, I gave this topic. So let me just take you through some few of my slides, which I standard slide deck that I use. So what is additive manufacturing? I think all of you might know, even though some of you or most of you are faculty and you might have worked in this area for quite long. So it is different from the other manufacturing process. Like you have typically you have your CAD model, which is the input for 3D printing or additive manufacturing, and then you do the tessellation and slicing, where you convert that into a triangular model and then slice them to get the number of layers, and then fabricate each layer together to get the final part. So you can start with a powder or a liquid, or you can start with a filament, or you can start with a sheet, right? So depending upon that, there are so many different ways you can process, right? So like if you start with the liquid, you can do a vat photopolymerization. If you start with the powder, you can do powder with fission, material jetting, and binder jetting. If you start with the filament, you can do metal extrusion. And if you start with sheets, you can do sheet lamination. Whereas this is like mostly like a direct energy deposition is when you start with typically a welding or coating or cladding type of process, or even sometimes we use cold spray and spraying type of technique. So typically all deposition methods. So you have several methods. ASTM classifies them according to starting raw material shapes, and these are ASTM classification or nominated process. Okay, so before I go into the topic of sustainability, I want to give you some basic background about what is sustainability and what is how additive manufacturing relates to sustainability. Before that, I will give you some general background. So I'm using some of the slides from Professor Michael Ashby. So he has written two books. One is on materials and sustainability. He is a very good internationally renowned expert on materials, right? So he wrote a basic material science book, as well as he wrote advanced material science books, process selection, material selection, and also written three books on sustainability. So he wrote a book on materials and sustainable development, also materials and environment, which are very well known to the people working in the materials domain. So you see, what is sustainable development? It is about 3P model, which is people, planet, profit, or prosperity, which is euphemized way for prosperity. Sustainable development means all the materials, products, design that you do should focus on environmental stewardship and also govern social needs of governance and management. So it should bring the sustainable development. So right now we are looking at 5P. So after the SDGs, right? So we have added people and partnerships. So it's like uh, we have partnerships and also planet and people and prosperity. So we have included all those 17 goals, which are having 169 sub goals on sustainable development. Okay, so this the term was coined by the Brundtland Commission. So she is a Norwegian prime minister who first gave the definition in this report. This report is by UN, United Nations, on the report of World Commission on Environmental and Development. So I think this was the first report in which she suggested the word, you know, she suggested the word our common future, right? So, which is typically a very interesting report where she coined the term. So, sustainability for her meant taking the needs of the present without compromising the needs of the future. Okay, so if you look at what is the relation between sustainability and additive manufacturing, right? So if you look at the top talks about all the milestones in the sustainable manufacturing, and the bottom one talks about typically um, the impacts of additive manufacturing into sustainability. For example, so the first one, UN Declaration on Human Environment, which came in 1972. So that is the time when the first additive manufacturing or 3D printing so-called process were under nascent stage. The first pattern came around 1984. So the word, you can see sustainable development is the word that became very famous in the year 1980, right? So, and then the word sustainable manufacturing or sustainable production was first coined in 1992. And in the Kyoto Protocol is when the industrial sustainability or industrial ecology intersections of ecosphere with technosphere was coined. And the 3R concept came. So then it has expanded to 6R by a professor from University of Kentucky. So, and then sustainable manufacturing first appears in 2000, and the Department of Commerce, the NIST lab, the National Institute of Standard Technology, they first defined the word sustainable manufacturing under the DOC, Department of Commerce report. Um, and then there is a lot of attentions on environmental impact of machining around 1995. People are trying to basically come up with some very good coolants which are environmental friendly, reduce the cutting forces, make some tool wear monitoring systems to prolong the life of the tool and stuff like that. So heavy attention sustainability in machining happened around 2004, and more attention on sustainability in additive manufacturing is by 2010, right? So which is like extended beyond 2020. Like so, you can see that sustainable additive manufacturing as moving beyond a certain 20. Now we are talking about how additive manufacturing gained a lot of attention around 2020. That is the time when it went up to the peak of the inflation, peak of expected uh, what you call as peak of uh, inflated expectations, right? So that's the time when the sustainability also gained a lot of prominence there. So if you look at sustainability of additive manufacturing, there are three aspects. You look at the economical dimensions or the profit or prosperity dimension, and then the environmental or planet dimension, and the people or society dimension. So talking about market evolution, novel applications, right? So supply chain restrictions and opportunities in supply chain, cost angle, right? So machinery cost, process productivity, and things like that. And then the resource consumption, waste management, pollution control, like what are the input outputs in the production process. And then social benefits, labor development, product quality, right? So ethics, and here comes the healthcare applications, right? So democratizing access to implants and also prosthetics, right? So and drug delivery devices and targeted drug delivery devices and regenerative medicine and those applications, right? So a lot of healthcare improvements, social from the social angle, from the public health perspective, and then copyrights, patents, IPRs, right? So those aspects are also covered. So this is the sustainability means like it is not about purely environment. So it covers all the aspects. It encompasses everything together. It's called sustainability, right? So what are the different ways the problem is studied? So in the literature, or you can say the published academic papers. So the environmental sustainability is the most studied among all other sustainability. Even though they have been studied, many papers have reported on sustainability of the social sustainability is the least studied, and economic activity is very less studied, very less conventional versus AM. So we have done few work. I will show you some of our economic and sustainable results that we have produced from our lab. And more importantly, I think I just saw your schedule, right? So, and one of my PhD student who worked on material efficiency, sustainability, is going to be a speaker, right? So his name is Reginald Elvis. So he's going to come and speak probably on different topics, but I'm also including some of his slides in some of his PhD work in my topic, right? So So let us just start with the material perspectives and then go to the design and then to the process perspective towards the end, right? So we'll start with the material perspective. So I think I'm also bringing in the timeline of materials. So if you see, so this is again from the book, right? So we have very recent modern materials like high entropy alloys, but it's this book was published somewhere around 2016. So many of them are not here. But if you look at functional materials, ferromagnets, peak PS, this is where the current research is largely happening. So polyamides have been well established. Like for example, I did my PhD in polyamide nylon, right? So that was my research way back in 2004. So I started with the polyamide, so almost you know 21 years ago, right? So that we printed a lot of parts and they are still durable. I could see them, function really well even today, right? So they're most durable polymers. And many materials have been not printed, like high density polyethylene has been not attempted, especially from the powder form, but they have been attempted in many other forms. Polystyrene has been used for vacuum casting and investment casting applications. You must have seen elastic materials like TPU has been in use, and high density polyethylene has been studied very well. But polypropylene is the least studied because of its rheological properties, making it not suitable for some of the applications. But if you see that, polymers has been one of the very well studied materials. Right now, we are looking at ternary alloys and binary alloys, and also using what you call as this high entropy alloys has gained a lot of prominence. And now, very recently, we started looking at critical minerals and critical printing, like last AMT call. So the Advanced Manufacturing Technology call wanted a lot of 3D printing applications for critical minerals and 3D printed critical minerals. Like some of the critical minerals that we have are rare earths, right? So how do you print rare earth magnets, 3D printing of permanent magnets, 3D printing of EV magnets, like magnets used in electric vehicles, right? So that has gained a lot of prominence. So those are the materials which has become much prominent in additive manufacturing. So and even you can 3D printed paper, even though paper was invented in almost 2000 years ago. So we started with the laminate object manufacturing where you can 3D print papers. So by stacking them together and laminating them together. So every material which could be pulverized in the form of powder can be 3D printed with a binder, right? So in fact, people have 3D printed a Mars sand. People have 3D printed, so many different other materials, right? So with a binder, so multi-materials, functional materials, graded materials, architectured materials, right? So designed materials, so-called structures, and then very interesting functional structures. So many different applications. We will talk about them in the design topic. In the material side, so many things are there. And currently, people are also looking at 3D printing of biomaterials, right? So, which has been there for last 30 years. So, in fact, if I vividly remember, my first exposure is Professor Weissen from Drexel University. So he showed me a 3D printed scaffold functioning in the human body. So way back in 2004. And he said in 50 years, people would be able to, around 2004 means 2054, he predicted that human organs could be 3D printed. So that was my first exposure to medical 3D printing. So, and then we did a lot of work with bone remodeling and trabecular surface remodeling, especially around, poly um, caprolactans, scaffolds, and also hydrogels. So we have done some work with Professor Basu from IIC Bangalore and also Professor. Um, so in fact, I reviewed their biomaterials course on NPTEL. So IIT, that time Professor Basu was in IIT Kanpur. So and metallurgy department professors who have established a US R&D network R&D center at biomaterials, right? So Professor Kantesh Balani. So their course on biomaterials is very famous, which I got an opportunity to review that course. So biomaterials is another important area where people are trying to print lignite tissues, uh, all kinds of tissues, nerve cells, bone tissues, even blood vessels, and some of the skin graftings, a lot of things, very interesting set of tissues. And then Currently, people are looking at protein patterning, looking to pattern the protein. So those are another interesting applications, which are not, these are industrial grade materials, and biomaterials and composite materials are the most research topic as of today. And composite materials are being used as exoskeletons, and then also used as prosthetics, right? So these are very interesting lineup of materials. So if you look at that, when we talk about sustainability, we talk about natural resource depletion, right? So how much fast we are consuming some materials, and how the sustainability of those materials will be there, how additive manufacturing can address. For that, if you look at this is the annual world production, so you can see that right now steel is the highest, oil and coal. I think today, from yesterday, a lot of geopolitical news is about oil and coal, right? So oil, steel, and gold is steadily declining because of the non-availability of gold in the earth's crust, right? So they have to dig deeper. And polymers, polyethylene, polypropylene, these are the commodity polymers we call, right? So they are mass produced in large volumes, so gigatons, right? So you can see gigatons of PET and polystyrene and polyvinyl chloride. So, and you might also know that 3D printing is not restricted to only metal or ceramics or polymers, also for concrete. Today, if you look at people are 3D printing houses, right? So concrete is another major material that is being used, and these are like as equal as oil and coal and gas, right? So these are materials which are completely 3D printed as of today. Like you have seen a lot of habitation rehabilitation centers in India itself. We have 7, 8 startups who do a lot of these 3D printed houses and 3D printing of concrete, cement, asphalt, and brick, and things like that. So you can see that if you look at the carbon fiber is another major 3D printed object which is going to gain a lot of prominence. So if you see, this is the world production, right? So that means if you have lots of opportunity in terms of additive manufacturing, if you employ this, how possibly you can address sustainability of these issues, because they are steel is available in abundance, right? It's on earth crust, so we don't have much problem. But we have problems in terms of rare earths. This is where the problems are there. The rare earths, titanium, magnesium, nickel alloys. So these are specialty alloys. Sometimes are there highly reactive materials. Sometimes they are highly corrosion resistance, and sometimes they are also very difficult to process through conventional routes and stuff like that. So, and Tamil Nadu especially, I have been reviewing a lot of Anna University thesis lately. I find amusing to see a lot of people work on natural fibers. So that has been very much of interest. I don't know, Tamil Nadu somewhat had this they've created this interest among people to go for all kinds of biofibers, like fibers which could be derived from natural sources. They feel it's very sustainable to do it. So natural fibers and man-made fibers both are, continue to be used, and they have this annual production of 10%. So look at the opportunity that additive manufacturing brings in terms of the materials, what the industry really wanted, right? So I'm just trying to compare from the how we have designed our products, how different kinds of materials are getting embedded. So if you look at a typical bulb, right, so which is synonymous with innovation. So whenever we talk about innovation, you use the symbol bulb, right? So it has become synonymous because it has a Edison, brought the bulb to fruition after so many failed trials, like 3,000 trials he made, and then finally he could sinter the tungsten, right? So which is the very important material that he used, which is the critical material, right? So you can see this is the only critical material that has been used in the bulb in the year 1920 from 2020, right? So almost one full complete century, right? So, and currently if you see, we have moved from CFLs to LEDs, so we use a lot of um, you know other materials. Like for example, we use all this rare earths right now in the bulb, right? So that means like we have our dependence on rare earths have increased a lot, right? So that means we have very small amount of them, but we are utilizing in one generation. So sustainability is getting affected. So we need to reduce that rare earths. I think you might know that rare earths are the point of contention between two countries, so at the brink of war. So the country which is trying to help stop the war, they say that if you give us rare earth, we'll try to defend you in a conflict, right? So it has become a conflict material other than the critical material. So it has become a conflict material. So that is a very interesting outlook. Look at the telephone, right? So these are some of the elements in 1950s in telephone. If you take a mobile phone now, you can see the amount of critical materials that we use in the phone is so huge. So you can see moving from no rare earths being used in telecommunication to the amount of rare earth that we use, right? So until otherwise we have a processing method which reduces its use or it allows its recycle or extend it, prolong its life, right? So are able to do a circular economy around these rare earths, we are going to be in trouble, right? So already, so one country has a lot of dominance in the critical materials, right? So I think in the last 1 year, Indian government has pumped in more than 17 lakh crore of money, right? So I think currently there is also going to be a call. ANRF is going to release a call for project on rare earths. 3D printing is one of the route that they see. So you can get up to 40, 50 crores very easily if you are interested in 3D printing of rare earths, right? So that is the most important material that people are trying to basically, save for the future generation and also cut down our geopolitical exposure and risks in supply chain, right? So that's the take. So again, you can see aircraft engine. So this is the early aircraft engine, right? So, and then if you look at the critical minerals here in the modern aircraft, right? So you can see some of those niobium alloys and ytterbium alloys, right? So and cobalt and tungsten and lanthanum. You can see so many different new materials are being used, and all of them are 3D printed. So imagine, some of the aerospace applications. Involving very complex 3D printed rocket engines. So most of these materials are being printed in bimetallic applications as well as in a multi-material graded structure. So to gain dominance into hypersonic cruise missiles, long haul aircrafts, more functional part consolidation. So rare earths are going to be the future of additive manufacturing, and sustainability is a very important key factor in that, right? So also we look at the energy consumption to just get an idea about where these applications are going to be there. So because energy is very critical, so we are going to basically move sustainability. Like we all know that process emissions constitutes a lot of CO2 emissions, which comes from fossil fuels, right? So we burn a lot of fossil fuel today. So we are slowly moving towards renewable energies like nuclear energies and also this is the world electric energy consumption currently we have, right? So if you see that we are still dominated by the fossil fuels, and India has done a quite tremendous job, and especially Tamil Nadu. So 40% of our energy mix comes from renewables, and we are actually having a target of moving to 100% renewables in another 20 to 25 years inside Tamil Nadu. But we already have a very good plan for solar and things like that. So India is also marching. By 2070, they want to become net zero, right? So it's a very good target. I think that is going to happen. So we have lots of opportunity there as additive manufacturing, which reduces the process chain, right? So already if you see it compresses the time, it reduces the process chain, so it has got a lot of advantages in terms of energy use, right? It's reduction in the energy consumption, having more energy efficiency and things like that. And as I said, the emissions, right? So, which is primarily coming from industrial production, is around 35%, depending because energy is a proxy for emissions. So, we take energy consumption in kilowatt hour, convert that into CO2 emission, and then allocate them to various impacts like global warming potential, ionization potential, and then water eutrophication potential. The SOx, NOx, and CO2 emissions are being used to compute the final impact, right? So that's the reason. So 35% energy consumption, and if the energy mix is very poor, if it's heavily dominated by fossil fuels, we'll have more emissions. So we need to cut down on process emissions, especially around manufacturing process, which are highly energy intensive, right? So that's the need. And this is the global change from 1975, how different, you can see that growth of the global trade in gross domestic product, right? So, and in comparison to the all other factors like, energy use, right? So this is the energy production is around 1.9% growth. From the index, if you take 1975, so you can see that this particular graph is not coming down; it's growing up. So we have a larger need for us to reduce the sustainability. So Professor Ashby talks about this particular framework. He talks this as a six headings for fact finding, right? So he talks about materials, typically from how we design a product or use material in a process, and its impact on energy, environment, and society and economics, which is the sustainability. But also he considers the energy and legislation as a separate fact, because we know that we are living increasingly in a regulated world, right? So we have lots of regulations like restriction of hazardous substances, RoHS regulation, REACH, restriction of hazardous chemicals, and evaluation of those things. And then we have hexavalent chromium emissions, lead, bromium, right? So mercury and things like that. So we need to have lots of legislation and also emission norms like Euro norms and other norms, which actually makes the product discovery, product development needs to be much faster. Product needs to be upgraded much faster. We need faster methods of understanding. So AM develops this particular works in this sphere, in a much better way compared to conventional manufacturing. So if you look at that, supply chain security, material availability, ethical sourcing, ethical manufacture is part of the materials pie, whereas resource consumption, water availability, emissions, and global forms the part of the global impact, right? So, and economics is about financial resources, cost versus benefits, right? So, internalized versus externalized costs, right? So, and then the regulations, laws, standards comes under legislation, and then energy, like how we are efficient with respect to that, right? So, and more importantly, when you look at the supply chain, so it's all about the moving from bill of material to bill of substances, right? So we need to understand what's going in our production process and things like that. So, and also material supply chain, and then vulnerability of supply chain. So I think we are now at a very important stage, right? So even though this slide is from 2014, it applies promptly today because China is controlling its major supply chain risk in the rare earths and things like that. So we need to substitute new materials when the materials become unavailable. We need to redesign the product. We need to rethink on production process. So also we have seen that the industrial index from the economic point of view, right? So the commodity prices have gradually come down over the years, right? So it's 8% annual growth. So suddenly after 2020, we can see that it is starting to, the industrial index is starting to increase, right? So this has become one of the things. And then we have so many risks in the supply chain, especially from the materials perspective. So mitigating this supply chain risk is very important, right? So the first way to mitigate this risk is to localize the production, right? So I think American manufacturing companies are putting in billions of dollars into additive manufacturing, primarily for reshoring. So they want to bring the production or manufacturing back into their shores. So instead of centralized production, they want to decentralize it or distributed manufacturing. So additive manufacturing sits well in that particular realm, right? So it helps people to basically, reduce their price volatility risk and geopolitical risks, conflict minerals risk, legislative controls, right? So, and also CSR, right? So it increases the brand promotion, corporate social responsibility, and also abundance risk. So sometimes having more material is also a risk. For example, when China, you know, dumps cheap steel into the global market, so every company will absorb that price risk, right? So abundance is also a risk, and scarcity is also a risk. So you need to have a constant supply of materials, right? So that's the so this is the emerging materials, right? So, and also if you see the EV has spiked the materials, right? So after EV has dominated, you can see cobalt as having a lot of price dynamics. This is done per dollar per kg over the years, and copper. And recently we have done a lot of research on copper 3D printing, especially around electronic 3D printing for copper conductive paste and things like that. So, and also applications involving biomedical, where physiological monitoring using strain gauges made of copper, antennas made of copper, And then also ECG leads made of copper and things. So we have done a lot of work on 3D printing of copper using direct writing and also powder sintering. The copper prices also dominate because copper is also used in EVs. The motors use a lot of copper in the windings and coils, and neodymium for magnets, right? So because neodymium alloys are used as ferrous materials along with neodymium forms the magnet. So the EV growth has made the prices fluctuate. So it increases and then decreases. Currently, the prices are much, much higher than what is being projected by Professor Ashby in this slide, right? And also the critical materials, as I said, cobalt and indium is available in Canada, beryllium, molybdenum in USA, right? So you can see a lot of this prominent, dominant countries. But China controls, you can see the rare earths. So they built up the entire supply chain. So if you see that, antimony, beryllium, gallium, graphite, germanium, indium for semiconductors, for manufacturing of chips, for manufacturing of EVs, for manufacturing of heavy industrial equipments, research equipments, you need. So they built the monopoly in many things. So it's not just about the availability of ores, but the processing. So they have perfected the processing route. So that China dominates 80% of the market of the rare earths of these materials. And some of the African countries where DR Congo actually mines cobalt, which is used in lithium-ion batteries, and platinum, which is used in a lot of biomedical applications, and tantalum being used. Niobium alloys are used in a lot of medical implants and applications. So tungsten being used in a lot of rare earth related applications, right? So coating and things like that. So you can see cobalt being used, and cutting tools are being made from them. A lot of other interesting applications. So Russia controls the gold mines and things like that. So this is one. So there is an index which is called Herfindahl-Hirschman index, which is nothing but sum of squares of their market share, right? So let's say, for example, if you for a rare earth, like imagine that which is having a very low HH index, means they are very less vulnerable to supply chain risks, because so what happens, like let's say you have 10% market share each country, that means point on square plus point on square plus point on some, add all of them, so that means that number is very low. Suppose if it's one country is having the entire supply chain, right? So that means one. So any material that is very close to one has a very high risk of disruption. So rare earths are now concentrated. There are only few countries which has the capability to produce rare earth. For example, nickel is the lowest because nickel is widespread available. Titanium, copper, molybdenum, lithium, cobalt. These are the materials which are having very low H index. For example, these are the materials which you see the HJ index is very high. So you can say that this is a low risk of monopoly action. This is a very severe risk. Anything about zero point 0.5 of the Herfindahl-Hirschman index means like they are prone to very high risk, right? So this is, I think someone had rights to write on the slide. So would you please not allow people to, can you revoke the rights? I think some people are writing on the slides. So please don't allow them to write on the slides, so which may be disturbing for others. I hope the organizers would take care of it. So this is the Espendahl index. And another important thing is you may have a conflict zone. So this is a 2013. Today, I think the conflicts have been shifted to Eastern Europe, where Russia and Ukraine is fighting, where the rare earths are very much concentrated. In fact, the war is more dominated by the rare earth conflict, right? So yesterday, we have seen some Venezuela, you can see, which has become the talk point. So Venezuela is another country for oil. So it is the conflict zone where currently it's under pressure. Colombia is under pressure for a lot of rare earths, right? So, and if you see in Africa, these are the countries which has very high deposits of essential materials, but they are under conflict. So this is around 2013. I think somebody needs to. I don't know whether I have the control. I don't know whether how to stop people from annotating, right? It is possible. So
Dear
please.
participant, please, sorry for interruption, sir. Yep. Dear participants, please, yeah, you please take care of your mobile. I think some mistakenly, I think they are doing, sir. Sorry, sir.
I understood. Yeah, understood. So I think you are using the option called annotate. So I don't know whether it can be disabled. So sometimes it
Yes, let me check.
repeats.
Sure, sir. Sure,
Yeah,
sir.
please. You can disable it, I think.
Yes.
Anyway, from the coordinators can. So you can see that West Asia also has lots of very important materials for EV, right? So, and also has oil. So these are oil-rich regions, right? So this is also another oil-rich region. And China controls the dominant supply, but there is no conflict as of now with Taiwan. So once that conflict begins, the world will see a very huge disruption in semiconductor because Taiwan has established TSMC is the monopoly for global supply of single crystal silicon and integrated chips, right? So they control the entire supply chain there. So is it possible I can clear this somehow? Let me just see. Erase. Because they are not moving, so they are there in the even next slides also. Okay. Anyway, thank you for giving me some time to erase this. I don't know. I think you should stop doing that if you are unknowingly doing it, right? So you have
Yes.
some issue. For other participants, it may feel right, so
Yes,
they may
sure.
not feel comfortable. So I talked about regulations, right? So there are, I think European Union has a lot of regulations. They are the first one. California is another state which actually has highest number of regulations in US. This is the most regulated state. So the REACH is the one that I talked about, regulation, evaluation, and analysis of chemical hazardous substances. RoHS is restriction of other substances. End of life vehicles, right? So there's a mandate policy. And then European Union directive on e-waste and things like that. So there's a lot of interesting regulations there. So every country follows. Our country also does a catch-up game. We have the Euro emissions and Bharat emissions. So a lot of regulations have been there, especially around environmental sustainability and environmental manufacturing sustainability. Right? So, and there are other rules like product rules, CAF rules, and chemical challenge and other things are there. So regulations are evolving and things like that. In fact, I was the convener for BAS, Bureau of Indian Standard for Sustainable Manufacturing Standards. So I think we had already 5 meetings. They're going to also come up with some regulations in Indian manufacturing sector. So we have like a very good committee which is working on regulations for Indian manufacturing segment, especially around sustainable manufacturing practices. So as we talked about, rare earths, right? So as we very clearly say, oxygen is abundant, right? So these are the materials which are rarely available. If we use them in one generation, and then we will not left with these materials for any future use. Right? So we can, science can somehow chemically synthesize them at some point in time, but it is very difficult to synthesize new materials, right? So new metals in the purest form, right? So elements in the purest form. So these are the availability of the abundance of under earth crust, right? So you may have to dig deeper, you may get more materials, but these are the ones that are easily available. So these are the ones easily available. These are the ones which are very rarely available. So we need to take care of them, and many of them we are using at a faster rate. Our rate at the concept that we are doing, so we may deplete these materials even in one generation. So we need to slow down, or we need to look for process. We need to do material substitution and things like that. So that is the thing. And look at some of the 3D printing process, right? So it's a holistic picture. So it's not about just materials like critical materials, minerals. So you can see that, with respect to materials, we have to look at a lot of things. First one is the particles emitted using 3D printers, like formation of nano-sized particle. For example, the first metal 3D printer that we worked on, we used to wear a gas mask, just like people working in chemical industries, right? So we cannot inhale the nano-sized powders. It forms readily a cloud, titanium powders and all. Safety precautions are, and they also form an explosive charge. So when you work with metal additive manufacturing, you need to be really careful. So we use a lot of vacuum cleaners with the vegetable oils to filter out those particulate emissions, and we need to treat them before we let out the fumes and outside things like that. So there's a lot of metallic polymer ceramic particles, right? So if some of them can get into exposure, so you may get a pulmonary exposure, or it may go into your intestinal tracts by mixed particles in your nails and things. Sometimes it can also go into emission to air, water, land, and then it can go into the thermal or skin absorption. So a lot of particle emissions are there around 3D printing. So, and another important thing in sustainability is how do you control? This one is, I think, a work done by one of my past lab. It's not. It's one of my colleague, but he was with me at my previous job, right? So his name was Monir Helu, right? So he did this work where he looked about promoting the circular economy through development of symbiotic networks, right? So industrial symbiosis is a term where you try to feed your waste. So instead of defining a waste, anything that you develop as a waste could be reused. For example, additive manufacturing might not produce much of the waste. So, for example, 3D printing reduces the chips, and it reduces the digital to analog to again digital conversion, because it is mostly digital to digital, right? So there is no intermediary patterns or dyes or molds or reactive agents and coolants. So there are no chips wasted. So it's like a lot of, it's mostly material efficient, but the production of powder sometimes may consume a lot of energy, right? So that's the only thing, right? So it can be reused. Most of the powders can be reused with the refreshments, like new powders. You can mix it and then use it. For example, selective laser sintering. Um, it produces waste polymer powders. Wool, scrap feedstock, metallic scrap, plastic polymers. It also produces a lot of biological waste sometimes. So fused filament fabrications also produces this waste, which you can build as network. For example, recently we have seen a lot of pallet printers which accept recycled plastics. You can put in the form of pallet. You can extrude filaments and then directly print them, right? So those kinds of symbiosis networks where the waste is fed into another machine to do something else with that, right? So these are some recycling and reuse type things. So you can see biological waste can be reused in some of the 3D printing of biological material, biomaterials, and things like that. So these are some of the things. Okay. So now let us just look at from the life cycle perspective. So far we have discussed about materials. Now we will discuss about the life cycle perspective of AI, right? So product life cycle means you have material extraction, processing, manufacture, use, disposal, and landfill. So these are the different ways in which you can stages of life cycle. So any material that you use in manufacture is extracted from the earth and processed and then transported into the manufacturing factory, and then stays in the product for some time, and then it is getting either going into the landfill, or it is going into the incineration plant, or end up recycled in a plant, right? So this is what it is like. So in life cycle assessment, people try to basically analyze the impact of the our human actions on the environment as well as economic aspect, right? So it is purely for environment. So it has got several the evaluation and relevant environmental, economic, and technological implications from cradle to grave is called life cycle assessment, right? So life cycle analysis is a very well known method. So last 30 years, people have been using it. It was developed by CTAC, which is called Society for Environmental Toxicology and Chemistry. So you can use it to identify the energy, material, and benefits, and also assess the impact. You can also use to evaluate and improve the plans, right? So it actually has a four-step method. It starts with the goal and scope, and then it goes into interpretation, inventory analysis, and then impact assessment, finally interpretation. So in goal and scope, what you do is you define whether you want to compare two products, compare two manufacturing methods, or compare one manufacturing method for different materials. So you can choose your goal and then analyze the inventory analysis, like how do you, all the inputs and outputs are assembled in inventory of flows. These are nothing but flows of materials and energy, and flow of waste, right? So you document them for each of these manufacturing stages or process or products or system, right? So you can build it, that you can define that boundary, that is called system boundary. You can draw cradle to cradle, or cradle to grave, or cradle to gate, or gate to gate, or gate to grave, right? So you can do many different types of such analysis. So then you do the inventory results, then you do the modeling of the impact to the assessment of impact to the environment and damage to resources, depletion, ecosystem quality, and human health, human toxicity potential, and then also plant toxicities, and then marine toxicity and things like that. So you can then come up with one indicator that can tell you whether the process is sustainable or not. Right. So the framework was developed in CTAC, right? So, and there are several workshops held in Netherlands and United States. So people have further standardized this in ISO 14040 series, right? So it's a good environmental decision making tool, which can help you to basically make decisions about a product whether it is sustainable or not, right? So, and you can actually use several functions per kg of FDM produced part, per kg of select releases sintered part like that. You can have per kg, or sometimes you can also have product attributes like so per employee of Apple uses per employee to do LCA, right? So like that you can use any other functional unit so that you can impact assessments can be controlled. For example, automobile companies use their per vehicle produced and things like that. So you can just use any functional unit and weigh them. So why it is important? Because it helps to identify what is the best alternative among two alternatives to select, right? So, and it will also reduce the environmental impact, not just in one stage, but consider the entire full life cycle stages. So that's why it is important. So here you can see two examples from the textbook. So the material intensive product, which tells about, this is typically like any product that is highly material intensive. There, if you see, the impacts will be much higher in material stage and the recovery stage. In between stages will not be having high impact. But if you use a use intensive product, for example, you buy a car, you drive for 2 lakh kilometers, right? So for a 10 years period or 20 years period, and you keep that, you will use a lot of gas guzzling sedans and gas guzzling, what do you call this? SUVs, right? So they will tend to use more fossil fuels and petrols or energy, electrical energy in EVs, right? So they would tend to get high energy impact or high impact in the use case. So you can see several life cycle phases. Each of them absorbs different kinds of impacts in different ways, depending upon whether the product is material intensive or use intensive. For example,
Yeah.
look at something like a diaper, right? So for a diaper, you would see that typically, it's a use space is very limited. So you just throw them after one use, right? So things like that, single-use products, they may have very low impact, but they will have very high impact in the recovery and material state, right? And if you look at the AIM, additive manufacturing, right? So what are the technologies that people have used to study LCA, life cycle assessment? So they have studied all the powder bed fusion process, like selective laser sintering, and electron beam melting process, laser beam melting process, powder bed fusion, and laser engineered net shaping. All those powder-based process and filament-based process and liquid-based process, they are all studied. So if you look at LCA dimension, they have done cradle to gate. That means only some stages from, let's say, from raw material extraction to manufacturing, or gate to gate, only manufacturing, or gate to cradle, manufacturing to the final recycling stage. So they have done this, and then they analyzed all the flows: energy, material, water, waste, emission flows, all the flows. They use several methods. For example, the Impact 2002 is one of the models that have been widely used. Recipe is another method for impact assessments, and midpoint assessments and endpoint assessments. Midpoint means like if you convert only to CO2 emissions and assess them, so that's you're not taking them to the global warming potential, then it's a midpoint impact. If you're taking it to the fullest final impact, then it becomes endpoint impact. So that is typically there. Recipe is like another one. CML is like developed by IPCC, has also developed a lot of models, Intergovernmental Panel on Climate Change. And there are a lot of databases where data is publicly available for many different manufacturing processes, but additive manufacturing is very limited. People are trying to develop this inventory databases. So they contain all this inventory of flows for you to build the flows and then model the sustainability very easily. So Eco Indicator 99 is a method which can, the one that we saw, the damage to ecosystem, damage to human health, and damage to resources. Eco Indicator 99 gives you one simple indicator in MIL units so that you can compare products in one single number. So it's a quantifiable way to compare sustainability. So a lot of categories: midpoints, endpoints, downstream, ILCD, and damage is what Eco Indicator 99 does. EMR does endpoint impact. Eco Invent does midpoint level, right? So like that, you have lots of these things. So this is one example of recipe endpoint analysis of an FDM process, right? So if you take a fusion deposition modeling, which is a filament-based process, you can see these are like endpoint impact in points, PTS, right? So which is one single indicator for you to study the sustainability of it, right? So if you say if you use a FDM process with the maximum material utilization, so you can see it's having the lowest impact. But if you use inkjet with the maximum utilization, there's highest impact. CNC parts has also got highest impact. You can see also the different components. CNC produces a lot of waste. You can see the waste is much higher here, right? So this is the allocated for manufacturing, because allocation means you are allocating the impact assessed to various life cycle stages. So which stage had the highest impact that you can compare here. So electricity use is also allocated here. So you can see that a comparison and then say that, with the endpoint, how the impact of each of these processes. You can compare. Now you can see that, FDM to inkjet manufacturing, which is binder jetting to CNC, you can very easily compare. And sometimes when you part are combined together, how the material efficiency improves. And if you make completely solid parts without any infills, density reductions, how much happens? Material efficiency is like how poor to that. So you can compare with life cycle assessment. Here is the very good comparison between four different aspects. First one is the AM, additive manufacturing. Then additive manufacturing included with the end of life assessment, like recycling impacts. And then conventional manufacturing, and then conventional manufacturing with end of life. So conventional typically means CNC machining. Here you can see different methods of analysis. It's a midpoint, taking the climate change, and no, like there is a weighing is like
तो
kilograms
स्टेचू
CO2
सर्किल पे है
equivalent.
सोमवार को वो जाम
This
लगा
is SOx emissions, and this is fossil fuel depletion. This is particulate emissions, PM2.5 equivalent. So you can see each of them has different functional units and functional impact assessments. So everything is converted into different units. For example, ionization potential, global warming potential, fossil fuel depletion potential. These are measured through that, right? So, and then O is it P, which is called ODP, right? Ozone depletion potential, which is measured in terms of kilograms of NOx emissions and SOx emissions and CO2 emissions and things like that. So if you measure in CO2 equivalent, that is a midpoint impact. If you take it to the depletion, for example, for infrared radiative forcing model is widely used to convert a CO2 emission to a global warming potential, right? So you have lots of these models developed by IPCC, which has been adapted to convert that numbers of energy usage, material usage into final impact assessment. So another important aspect which is less touched, as I said, is the social impact. So in terms of additive manufacturing, the cumulative of all social life impact comes typically from community engagement, right? So for example, local community, society, consumer, value chain, and worker. So I think additive manufacturing enabled fully automated machines. Like for example, when we were working with 3D printers way back in 2004, right? So I have seen people working in lathe and doing research in machining. They would have to spend with the machine for a long time. So we don't do that. So we just switch on the machine. It runs for 36 hours. We come back. So we can do a lot of work parallelly, right? So it enables, like just like your AI is cutting down. So additive manufacturing reduces the hours of work, so like health and safety and socially beneficial. These are the different percentages of impact of total 100% of impact, how it impacted different factors, which one impacted more. So if you look at it, local community is the highest impact because people are able to democratize the manufacturing, decentralize and democratize the manufacturing. So cultural heritage, protecting 3D printer is able to protect the cultural heritage by archaeological models can be 3D printed, preserved. There is a complete ecosystem of scanning, printing, preserving, right? So like that, creating local employment, also safety and health and living conditions. Another thing is consumer, like so consumers get privacy, transparency, and end of life responsibility to recycle the components. Society, like for example, public commitment to sustainability, how people are behaving to 3D printed parts and things like that. So you can see, and also in the value chain, supplier relationship, intellectual property rights, how they would affect those. So you can see these are the cumulative percentage of social life cycle impacts measured across many AM processes. Here AM is very generic, but this data is very particular about consumer 3D printing, which is typically FDM. So this we have already seen, right? So this slide where we talked about, so shall I erase this? Thank you. So So if you see that we already saw that this particular slide, particulate emission needs to be looked at, right? So which is very important from the perspective of this fusion deposition modeling. Wherever you're talking about post-consumer plastic, like we have one of the very important thing that happened to 3D printing community, the DIY community. They picked up PLA, which is the biocompatible material, which is very less harmful to society, right? So compared to ABS, acrylonitrile butadiene styrene has a lot of harmful emissions. So you might know that in Hyderabad, somebody was trying to produce a styrene gas, and then there is an accident happened, and then huge deaths happened in Hyderabad. So, but it is styrene gas in isolation. But ABS is generally considered to be safe to use. It is biocompatible, but it's not advisable to burn them. If you burn those ABS, you get emissions, particulate emissions from styrene and all, which are very harmful, right? So even the fumes and vapors that are developed in FDM-based 3D printing using ABS is far more environmentally less sustainable compared to PLA, right? So PLA is from derived from natural resources, right? So it's biocompatible, and also it's a biodegradable polymer, right? So it's a very important that we use PLA for most of our applications. It has become very important that it has become more sustainable. That's the reason why additive manufacturing, especially around objects, around polymers with PLA, is more sustainable, right? So this is from the materials perspective and sustainability perspective. Now let us try to understand from the design perspective how sustainability is driven, right? So I think so. One of the things that additive manufacturing and ecological sustainability has come up with something known as eco design for AM, because design for additive manufacturing enables a lot of opportunity for people to explore, functional integration, part consolidation, hierarchical structures, multi materials, and stuff like that, right? So, but if you look at ecological performance of additive manufacturing or eco, so if you combine ecological sustainability and additive manufacturing, so we can look at the process emissions and then understand ecological performance, right? So if you combine design, which is eco design, so if you combine design for AM and everything together, it's called eco design for AM, which is considering the ecological sustainability of additive manufacturing, where you also consider these constraints. When you talk about constraints, right? So we always talk about simple versus complex designs, right? So we normally go for design changes, right? So when these are the constraints, we get to overcome these constraints to get a better design. So this is the design space, right? So, but Albert Einstein once said, right? So the design that works is the simplest one, right? So the best design is the simplest one, and also simplicity is like very important. So, but additive manufacturing likes complexity because it can introduce a lot of complex designs. So if you look at functional constraint, right? So like for example, overall size, width, space arrangements. So like for example, you have free moving parts, velocities, acceleration, kinematic between the parts. Sometimes the forces involved, and sometimes what type of energy is needed, like heating, cooling, conversions, and materials, how it is to be transported, properties of the materials, and what kind of control system you are using, electrical, hydraulic, mechanical, pneumatic, and also information flow like displays, outputs, a lot of functional constraints the product. So 3D printing can combine many of these functions together. Like for example, motion, it can combine forces, it can also combine and then make some functional things, right? So control systems can also be integrated into the part, like some of the ways, and also many parts like overall size optimized, space is optimized, and then geometrically, topologically optimized, generatively designed. The functional constraints are there. Safety constraints are also there. Like for example, this is another important aspect of dimension of sustainability is the industrial safety, right? So safety to worker, injury and illness prevention to workers, right? So that is direct hazard elimination, warnings and training, right? So environmental pollution reduction. And another thing is quality, right? So we need to have good quality assurance, regulation standard, because 3D printing is governed by a lot of standards, right? So qualification standards, reliability, and things like that, right? So, and a lot of manufacturing constraints from the conventional manufacturing, we see that waste elimination is very important. From you can see that most of the manufacturing, near net ship manufacturing, also produce waste in terms of other aspects like coolants, right? So chips and things like dyes actually would involve lots of dye release agents and harmful chemicals being used there, right? So the production of components, purchase of components, assembly, transportation, all comes under manufacturing concern in the design. And timing constraints, that like we need to have lead time. So when the production is, how long does it take for the production to start? What is the lead time? So design schedule, developmental schedule, production schedule. So timing constraints are another constraints. Another is economic constraints like design cost, development cost, manufacturing cost, distribution cost, all those things, right? So and then ergonomic constraints like having controls, layout clarity, user interface to be clean, man-machine relationships, right? So that is another important constraints in the product constraint, design constraint. And then comes the sustainability, most important part of sustainability, which is the ecological constraint, which talks about green chemistry and using raw materials which are less harmful, avoiding toxic substances, right? So material selection, working fluid selection, like fluid gases, which has less toxicity into manufacture. And another important thing is that when you do optimize all these things, additive manufacturing can also take care of this aesthetic constraint. So you can get more organic shapes. Your shapes could be you can function-driven designs, which could be having a form which is completely different than the other conventional manufacturing that is feasible. So having more organic, aesthetically pleasing designs, having very good class A surfaces, curves, and things like that. So these are aesthetic. And another important is, as we talked about, in the life cycle constraints. So talking about distribution, operation, maintenance, right? So like, for example, wear and tear of the components, right? So how long that product is durable, the durability aspects of that, right? So legal, I already talked about legal regulation constraints, like OSHA is for safety operations in the production process, because when you do fabricate something by welding, the Occupational Safety and Health Administration would involve huge regulations in terms of on federal aviation, federal drug administration, because all when you're talking about healthcare, there are a lot of regulations around healthcare. So you need to qualify your parts for use. You have to do a lot of clinical trials before you can bring the product. So legal and ethical constraints are there for additive manufacturing too, right? So as good as any conventional manufacturing, but the rules are a little stringent for additive manufacturing compared to conventional manufacturing, because additive manufacturing has recently being used to produce components compared to pedicle screws and other screws which are conventionally manufactured through machines which are entirely suitable for chemicals. But we are now looking at some of the reactive chemicals, which are used in the production of cobalt chromium implants and titanium implants. So safety there, even though biocompatible, but the production process has to be certified. The feedstock to the final post processing, everything needs to happen in a clinically proven environments, right? So, and then the intellectual property, right? So protection of the intellectual property designs, and because it's more servitized. Servitization angle, look at AM. So we have to protect a lot of design, because there's a lot of contract manufacturing happening here. And design for environment is the ability to minimize or eliminate environmental impact. So we have to follow certain principles. So there are a lot of more than I think 900 guidelines are available for eco design, right? So where you follow the design principle that minimizes the environmental footprint of that product in various life cycle stages. Right. So with that, I think DFAM, or design for eco design, start with first an introduction to DFAM. So DFAM means like design for additive manufacturing. When the design is suitable, when you are talking about design freedom. So design freedom is available in so many different ways. For example, here the part consolidation, and then increased complexity in the cooling channels, and then having mesoscale, microscale structures to in the hip implants, and then also bionic designs, like having designs which mimics the natural shape to do weight reduction and also increase life cycle impacts, because the moment when you reduce the weight of an aircraft or automotive, so it has got far-reaching life cycle impact. Even 1% improvement in the light weighting could impact life cycle impacts largely in the use phase, right? So weight reduction through additive manufacturing, through generative design, topologically optimized design, and things like that. So these are all things. So if you see that there are many different potentials. One is called customization potential, lightweight potential, internal channel potential, functional integration, part consolidation potential. So these are all different potentials which you can evaluate to come up additions. Because in fact, we have one of the PhD students in our lab. In fact, three of the PhD students currently working on decision support system. They are modeling this metrics, like all the potentials, come up with metrics to measure the suitability of additive manufacturing for environmental and efficient manufacturing methods, right? So to analyze existing design and then improve its sustainability by lightweighting it, making it more suitable for use in the environment or give life cycle benefits to it, right? So cost benefit analysis in terms of entire life cycle costing is being done in our lab to analyze these designs to see that they are environmentally sustainable and also potentially being used in end use applications where it demands less energy use in the use space. So I think this is one of the things that it also enables mass customization, meaning that coming from mass production, so we are moving towards mass customization, and we are talking about hyper customization with the recent generative AI algorithms,
Okay,
which
na?
can customize
From
designs
0
for
to 6,
individual energy
5
needs.
to
It can customize,
7.
right? So
And then
we are
వెయిట్
moving
చేయాలి.
towards more personalized manufacturing or personalized production coming from craft production to mass production. So Industry 4.0, 5.0, where we are talking about producing something more suitable for an individual customer, right? So that way the product life cycle improves, durability improves, and then one-off products can be manufactured, and then the variety can be improved, right? So this is the idea of this design freedom. When we talk about design freedom in additive manufacturing, so we move from the sustainability angle. Then the design freedom is additive manufacturing provides a complete design freedom, especially from the customization potential to increase design and geometric complexity to having mass and hyper customized parts, and at the same time huge variety, the variety, volume, and also mass complexity. So it is typically called complete manufacturing freedom, which comes at the same cost, whereas conventional manufacturing the cost will skyrocket, but here it comes at the same cost, right? So there are four different types of complexity that is being driven by additive manufacturing. One is called shape complexity, second one is hierarchical complexity, third one is functional complexity, and fourth one is material complexity. So this all these complexities are possible. So shape complexity, where you can have complex shapes to manufacture. Hierarchical complexity is where materials with hierarchical structures. So typically I could frame this as structural complexity, like lattice structures and hierarchical structures and things like this. Functional complexity for increased functional integration, material integration, multi-materials, and material complexity is another important aspect. So these are all the drivers, right? So these are some examples which I've been using in my slides for quite a long time. So some examples of optimized structure which could reduce environmental footprint, also provide a lot of design freedom. So light fitting, so this can fly a little longer because the battery capacity is very limited, right? So it can originally it has got 7 parts, now all integrated into one single part. The structure can fly longer. So this is the drone system which could be monitoring a spy drone or something like that. Right. So also it's a bicycle frame optimized for metal additive manufacturing with the reduced assembly, and then this component being optimized to reduce the energies. Like a lot of e-bikes have currently come up which can use this structure for reduced, increase the range of by e-bikes and things like that, right? So lattice structures, as I said, also reduce a lot of weight, increases material efficiency, also promote sustainability through that, right? So also provide a lot of design freedom. And functional complexity, for example, cooling efficiency improves, the thermal load decreases. So we need, instead of having a very large cooling towers, when you have instead of straight channels, when you have a conformal cooling channel, so you can see the weight is also reduced from 19.2 to 1.2. The footprint is also reducing to 85 mm from 210 mm. The total volume is also reduced from this to this. You can see that you can have multifunctional structural, thermal, fluid interactions. These functions are getting integrated into one single part, right? So you can see that this is the classical design and additive design. So it gives a lot of freedom. At the same time, you can see number of parts get reduced from 8%. So like you can see originally 12 and only 8% of the original number of parts is currently there. Only 4% of the original weight is there. Only 11% of the original volume is there. Completely removed gaskets, right? So it reduced the assembly time, throughput time, right? So the cost is also only 27% of the original cost. You can see that the design's functional integration, additive manufacturing provide a lot of impact there. And hierarchical complexity, where you can actually integrate multiple structures into one structure, which could give a lot of important inputs in terms of highest strength and weight, highest strength at a reduced weight, right? So these are structures like oxalatic structures for metamaterials, for biomedical applications, as well as for industrial applications. You can use these structures, right? So this is a rock control arm, so suspension control arm with the rack, with the structure with filled lattices, and also lattice structures are graded lattices. And material complexity where you can have composition, but this is a little difficult to get, but still metal deposition process can aim for varying percentages. Can I think it's called what do you call this as compositionally heterogeneous materials, right? So, and also electronic 3D printing, embedding foreign components like IC chips into the design, and then ability to design them having active passive components in it, and then the polymer part being again can be 3D printed with electronic applications, right? So in summary, you can see form or geometry complexity, hierarchical complexity, material complexity, and functional complexity, leading to higher value addition. So one important aspect all we wanted to understand is how much it improves sustainability. So there's a lot of improvement in sustainability. Everything culminates into cost reduction. So finally, ultimately improving the sustainability of the 3D printing. So the design freedom that we get is ultimately linked to the sustainability of the production process, right? So you can see that it reduces the material consumption, reduces the number of joints, time is reduced, and conformal cooling reduces the energy footprint, right? So weight reduction, ergonomics, flow dynamics. So when the dynamics, flow dynamics improves, less cooling loads, less drag forces, right? So, so all those aspects, right? So you can see a lot of improvement in cost, ultimately leading to improvements in sustainability. So there is also a lot of constraints in terms of even though we said DFAM is more opportunistic and benefits, but there are also a lot of constraints which is also to be looked at. For example, here in this case, even though the complexity is increasing for a TA64LB part fabricated using SLM, right? But if you see that after DFAM, you can see some components can even increase its cost. The cost is much higher. Even the design freedom, the original print to part ratio has been reduced. These are alpha, beta, gamma, which is the generative design, manually redesigned or topologically optimized designs can reduce the weight. This is the part weight in terms of 1 kg of original weight, and this has reduced up to 1.6% of it, right? So you can see only 1.6 kg, 1.6% of it, right? So you can see the print to part ratio has been there. You can see that the cost is skyrocketing. It is very much higher when compared to constraint based DFAM to opportunities by DFAM. So there's a varying degree of benefits that you get that we need to understand much better. So in our lab, as I said, we have analyzed these opportunities and constraints, right? So for that, we needed to have some metrics. So this is one of the metrics that we have developed, which can understand this complex, which is called shape complexity metrics for different types of parts. So design complexity can be measured so that we can have some numbers to prove that we get the higher complexity, so that the designs can be modified to higher complexity, and then that could be used in the additive manufacturing. So these are some examples of parts that we could analyze for internal shapes and external shape complexity. So with and without lattice structures, you can see the complexity of these parts actually increases with more lattices in, but also the cost reduces at a later stage. You can see this is the weight reduction versus the shape complexity. You can see G engine bracket can be having highest weight reduction possible, and it is also highest complexity, right? So that means like you can compare the cost versus complexity of this and understand the dynamics of different parts, and then able to basically make a decision whether to go for weight reduction. That could pay rich dividends in terms of use space, life cycle impact, and things like that. So, and a lot of new tools have come which can actually generate thousands of alternate design variation, like the one in generative design. This is a Fusion 360 which can generate, not Fusion 360, today we have more than 18, 19 tools which can do generative design through generative AI, right? So for example, this is the generatively modified G engine bracket with several variants which we compared. And we wanted to basically develop a methodology wherein we could, construct a decision matrix with the help of this four metrics: external shape, internal shape, incremental cost, and cost benefit ratio, to just make a decision whether to go for AM, which is going to be sustainable and energy efficient, and also it is technically feasible, right? So we can choose a composite complexity metric and aggregate that metric. So we did a simple cost benefit ratio of unoptimized to optimized design, but the complex calculations go in it, right? So the cost calculations is for LPBF, but we have to develop very complex, very fine granulate complex cost models that go, even though this equation looks simple, but the actual calculation of the cost comes at a very sophisticated cost model, which is hidden beneath, right? So we also did an incremental cost, which is like, cost after design optimization, right? So how much design cost and manufacturing cost and post-processing cost gets, incremented higher up. So we have seen that in that slide, even though you topologically optimize, but you introduce a lot of lattice structures, then you also get support structure, which needs to be removed, right? So then there is an incremental cost for, processing those support structure, removal of support structure, post-processing. So which could, increase the cost slightly bit, but the benefit is much higher compared to the incremental cost. That is what we studied here. So these are some example parts like upper triple clamps and other parts which you have studied. So you can see many design variants are being studied. If you see this topologically optimized designs, they are being ranked for external shape complexity, CES, and internal shape complexity, and also for cost benefit ratio, and also for incremental cost. You can see some designs, the original design is this, but you can see the TC7 has the highest incremental cost, meaning that it introduced so complex shape that it became difficult for it to post process. So it took a lot of time to machine that part, to post process that part, and to remove support structure, right? So, but some designs at the same time, TC7 also offers very high cost benefit, right? So you can see the same design TC7, which is also having high incremental cost, but also having high benefit cost in terms of life cycle thinking, right? So in terms of its use space. So that means spending this higher amount is worth if you consider the entire life cycle cost of it, rather than just looking at. So if somebody looks at it, 3D printing is very expensive, so we'll go with the conventional manufacturing. But life cycle cost wise, if you look at it, the benefit is not accrued in the conventional. Maybe the manufacturing phase, there you are able to address the manufacturing cost, but it has got far-reaching life cycle impact. Because, for example, somebody runs a gas guzzling sedan, reducing the weight by 1 kg will improve its cost, right? So these are some of the aspects. So we didn't then do use some kind of a fuzzy method to you know aggregate these four different, because these metrics are interdependent, right? So some is in cost domain, some is in design domain, complexity, geometric domain. So to aggregate them, we need a better composite indicator, right? So for that we used a fuzzy powered weighted Maclaurin symmetric mean operator, so which is used to get this external internal cost penetration incremental cost metrics shaped, because this is the dynamic weight that we use for that. So this is the operator which is used for aggregated matrix, right? So then finally we get this one single number. So we just rank them, right? So we are able to then analyze this for different complexity and also rank them using dynamic weights. So these are the dynamic weights for each of the individual designs, and then we get a normalized Hussey decision matrix wherein we could combine all this metrics and then take a decision on the ranking. So this is like we also did some kinds of sensitivity analysis. So we did use different kinds of criteria for how to assign these weights for the individual metrics like benefit ratio, incremental cost, external internal shape complexity. So we when you use equal weight, we get a different ratio. When you used standard deviation, we get a different ranking. When you use critic, we get different ranking. When you use entropy, we get a different ranking. Like if you see, they are almost um, similar in ranking, but only few things you can see that they have changed. Some numbers here, the numbers have slightly changing, but you can see they are able to maintain the ranking most of the time. But you get different numbers for the same ranking. So, but if you see, if like equal weights, if you give, normally what happens is like the numbers are very clearly able to distinguish, but it's not appropriate. So we use the critic method typically to analyze there. So this gives you the different methods also we compared. So instead of fuzzy powered weighted Maclaurin symmetric mean operator, how come if you use topsies or AHP topsies or simply weight reduction as a criteria or post processing cost as a criteria, how does the ranking? So then we would able to calculate the Spearman rank correlation coefficient and then see how the design freedom affects the overall improvement in sustainability on ranking over its entire life cycle. So we can just compare them using weight reduction. So cost and weight reduction. So for example, if somebody can say that, I cannot do weight reduction because it is going to, AM is going to be very expensive. But if you look at the total processing cost price, it may be much higher, but the overall life cycle benefit would be much. So we need to understand that a trade-off between them, right? So That's the approach, right? So, and then we are now focusing more into unit process perspective, so wherein we want to basically analyze each additive manufacturing process using a standard methodology. This is the methodology proposed by ISO 14955. So we use this methodology wherein we take a unit process like selective laser sintering and then understand its subunits and model their inputs and outputs from technosphere to ecosphere, right? So then we create a reference flow like 1 second of processing time for a specific load out of a unit manufacturing process, right? So 2000 hours a year, how does the system boundaries work? So the methodology is like this. So you have a goal and scope definition, just like any LCA. And then you have to do a energy consumption, resource consumption, and process emission analysis, theoretical and industrial process measurements. You have to corroborate and finally come up with a time study and then give the cost. And because time is money, right? So most of our costs are derived from time. For example, machine hour rate is like how much hours that machine is being utilized. So we calculate that by multiplying by the cost of unit cost of the machine hour rate, right? So a lot of these things involves verification and validation for the theoretical calculation. So this is the one example of CO2P methodology being used to understand the 3D printing process. So you can see the product design where the process parameter selection and powder steady average power production mode, how much compressed air is being used because we need to purge the chamber, right? So how much waste material is there? You can use the LCA method. So what is the layer thickness, build volume, height? What is the processing time? What is the additional time? So you can use so this is a methodology proposed by European universities. So there's a very big consortium called CO2PE consortium. So they use this methodology to collect data about 3D printing and additive manufacturing. Right? So this is one example of a metal additive manufacturing system modeled as inputs and outputs to technosphere and ecosphere with the several elements like laser system, subsystem, nitrogen gas generation system, heater system, motion and optical system. So we can analyze each individual elementary flows and then create the flows in that particular order, right? So this is the example of that particular idea from modeling the production process, individual additive manufacturing process, right? So and then you can also compare the specific energy consumption per unit kilogram of part to be fabricated in this metal. How much energy would be used? Like you can see specific energy consumption in terms of per kilogram. What is the consumption of them? What is the total energy consumption in various different processes for polymers and metals separately, right? So this can be also studied. And this is again specific energy consumption for metals. You can see that CNC machining has very high energy consumption compared to LPBF. Wire DD is little higher because it uses the arc as only 76% efficient, right? So whereas lasers are much energy, poor energy efficiency. Lasers actually CO2 lasers have only 6% energy efficiency. Wall plug efficiencies of lasers are very poor. That's why jewel printing and binder jetting comparatively uses very less energy compared to laser because laser is highly inefficient, right? So, and various life cycle stages are also shown, like different life cycle stages, what is its footprint and things. And then if you look at some case studies here, like hybrid comparatively, like, when you combine additive and subtractive together. So, for example, this is an additive plus subtractive process using, let's say, you have typically iron ore which is being transported and then in a melted and using a gas automation powder is produced and transported to a DED machine and then heat treated, right? So and then finished machine using CNC because DEDs are near ship process. Warm once produces it, then you have to take it for machining, right? So and then the waste powder being produced and electricity. So you can look at all the energy model flows. So this is again the same process, but if you see only CNC machine without having 3D printing. So what is the total comparison between them, right? So in hybrid additive manufacturing, you take a gas automation, a powder, and then DED heat treatment CNC. When it has a buy to fly ratio of very healthy, 1:34. In a traditional machining, the buy to fly ratio is very poor. That means like when you buy 5 kgs of titanium, only 1 kg enters into the flight. Whereas here, if you buy 1.34 kg of titanium, probably I think only 1 kg goes, right? So you can see the buy to fly ratios are much higher in hybrid additive manufacturing compared to traditional manufacturing. So, and this is a comparison of hybrid additive with the CNC, energy consumption with respect to all the renewable energy sources, and also the impact assessment. So the results of global warming potential, acidification potential, eutrophication potential, ozone depletion potential, and also the volatile organic components, right? So all those things you can see environmental impact of comparison. You can very clearly see that CNC alone could not produce environmentally sustainable, but when you combine them with additive manufacturing, you produce a near net shape. It always leads up to very environmentally efficient production. So sustainability of additive manufacturing is much higher. So again, you can see comparison between A and B, between part fabricated via CNC and then via DED. You can see the comparison between two different case studies, right? So raw material production stage, part fabrication, the processing energy is much higher, and organ production, raw material production. You can see two parts. This is pure machining, and this is hybrid machining. You can see that it's primarily material dominated energy. You can see finish machining is much higher, expensive. Tooling, transportation is much higher, expensive, things like that. So we also produce a case study, which I would talk about Elvis, right? So we did this case study of this. He wanted to understand between difference between the turbine blade and the impeller, right? So he took the data from Connecticut Center for Manufacturing. So they are kind enough to provide us the data. So we took the data from them. Also, we took the data from the CMIL lab from Penn State. So where we collected the data for DED process and also for powder bed fission process. So we are trying to compare the two case studies. One is a turbine blade and impeller. Three routes. One is purely through AM route, and then purely through CNC route, and then combining hybrid. So which is more energy efficient, material efficient. So here we are focusing on material efficiency. So here you can see total cost. There's a very complex cost calculation that goes into these equations, right? So if you look at impeller, which has got a 7 subtractive manufacturing, it used something close to $1,044, whereas it's like $7,000, right? So if you look at, we then did a very interesting approach we published long time back, where we wanted to basically see how hybrid manufacturing can be done. One, either you can partition as machining volume and additive volume separately, or you can, these are like very complex features can be done in additive, other features can be done in subtractive, right? So this is called feature based volume partition. We also use stock-based volume partitioning that I will show a little later, where we take a near net shape approach. We give only a proper allowance there, right? So if this is, for example, I think I'm running out of time. So I will take, with permission of Dr. Gopi Saravanan, few more minutes to wind up. So I hope I'm
Yes,
okay to take 2 more minutes.
yes,
Yeah, okay. So this is the total time study between the volume partitioning approaches, right? So you can see total time involved is 306 minutes and 310 minutes. In additive manufacturing, it is 108 minutes. In subtractive manufacturing, it is 190. So you can see larger time, and also impeller, but the time is reduced in impeller, right? So the total time, because it's not that complex, impeller can be much easily produced compared to turbine blade, right? So again, you can see cost incurred in additive and subtractive and hybrid. All three are compared. You can see that I have the graphs, so I'll show that. This is a stock-based comparison. We also did. Suppose what happens is, like, you make near net shape, give 15% or 10% stock or whatever percentage, right? So as machining allowance, you make the near net shape and then machine it to that, right? So that means you have AM and then 15% stock that is to be machined as the volume that is to be done, right? So in that case, if you see the cost comparisons are there. This is a very data I skipped because for the brevity of time. So here you can see this is a sustainable. This is the subtractive manufacturing. This is hybrid additive manufacturing, but it is based on feature-based volume partitioning, where I am partitioning complex features, apportion them to AM, and then simple features to conventional manufacturing. So it is heavily, the contribution of the material cost is much higher in subtractive, whereas the total cost comparison, the material cost dominant process or conventional process, where I could see that it is less to do with materials, even though the total cost, it's only 100% share. I'm not talking about the absolute reduction, or I'm talking about the percentage contribution of material in the total cost. The total cost may be different, but I'm only talking about the contribution of percentage of the processing cost is much higher here, whereas compared to the material cost. So we are trying to bring down the material cost, material sustainability as a much better aspect here. Very similarly, you can see that for impeller also. So when you combine hybrid additive manufacturing, so you can see that the stock-based, we are able to reduce the material cost, right? So here you can see that, out of the total cost, so $631 has been reduced to $156. Huge savings, right? So that's why companies are heavily investing in hybrid additive, because they could combine the best of the both worlds and get a lot of reduction in the cost, total cost, right? So That is the idea. So these are some data sets which tells about the material efficiency. This is the final slide. And bite to fly ratio. If you see conventional manufacturing, CNC machining, turbine blade, right? So you can see it's 13% material efficient, whereas impeller is 23%. But in hybrid, you can see material efficiency improves to 87%. It's a very, a large increase in material efficiency, which you can see. The bite to fly ratio also, you can see. I showed 5.3 kg, right? So in the first slide, here you can see 8.3 kg of titanium. If you buy, only 1 kg goes into the final flight in the turbine blade, right? So here, if you see in hybrid AM, it reduces to feature based, it reduces to 4.4. But when you do stock based near net shape, right? So it reduces up to 1.5. That means only you buy 1.5 kg of solid stock material, right? So for conventional aluminum, imagine that you are going to get 1 kg into the flight. So imagine that there is no chip being wasted here. So because you're only 15% chip being wasted compared to the entire very complex solid block of titanium that you have to machine, that you waste the material, 90% material as a chip. Yeah, this is the biggest advantage, right? So that's why hybrid AM approach with the stock based is paying rich dividends in terms of cost and material efficiency in both cases. That with that, I think I would like to stop. I know that I have overstepped my time. So because we need to also interact with the participants for any questions, right? So if you have any questions, you may want to ask later because the other speaker might be waiting because there's a back-to-back without any gap. There's going to be another lecture at 8, I believe. So you can write to me, or if the organizers allows, I can answer a few questions in this topic.
Yes, sir. Thank you, sir. Thanks for your highly informative and mind-blowing talk. So we have learned different domains in additive manufacturing, especially aerospace and mechanical, automobile, and biomedical, even biomedical applications. So